Yeah, so this is the Biomimetic Robotics Lab, and mainly what we focus on here is both developing hardware as well as the controllers for a lot of dynamic motions. So the history of the lab is kind of in this little museum over here. So we have Cheetah 2. This had the land speed record for an electric quadruped for a while. This here is Cheetah 3, and this one, there's about a lot of blind locomotion work going into there where we could walk up steps and do a lot of other cool dynamic motions like jumping. The most famous robot we probably have is the Mini Cheetah, and this was developed around 2016. And the whole idea here is let's take all of the cool technology that we've innovated on with these two robots and miniaturize it into a form that we can distribute to a bunch of different labs around, but also design it in such a way that it's a lot easier to do research on. And then all of that sort of transitioned to the MIT humanoid, which we have over here. And this is sort of just another sort of like scaled down version of a full-scale humanoid. So you'll notice that it's actually really short. It's about like the size of a toddler. This thing is capable of jumping, like half a meter off of the ground. It can do backflips. We were able to get it to do full backflips and everything. We have walking policies, reinforcement learning policies, a lot of model-based controllers as well. The manipulation platform. We have this nice robot arm, which was also designed in-house, and also this nice articulated gripper. But the cool thing about this gripper is we have these tactile sensors on the end, and so we can get a sense of touch. And these, interestingly, are designed using an elastomer, and then there's barometric pressure sensors on the inside, which is the same thing that you have like inside of your phone. Pretty cheap components. But the way that we're able to tell where all of the contacts are happening is actually training a neural network. Imagine if I'm pressing on this sensor, we don't really know exactly where all the different pressures are going to be read at the actual barometric pressure sensors inside on the PCB. But using this learned model, we can create that mapping, and then using all of those different readings from within the sensor, we can get a sense of where on the finger it's being touched, and also with what magnitude and all of that. And we can use that within our controllers to develop nice reflexes. For example, when I pick up a ball, I don't really have to look at it. I can kind of fumble around and figure out how to hit it or to pick it up using these innate reflexes. And we're trying to sort of build all of that into the way that we control robot hands, which is kind of a new paradigm shift. Because traditionally a lot of manipulation, you look at something, you do a lot of planning, you go in and reach and grab it, but if you fail, you kind of have to start the whole process over again. Whereas our idea here is we can potentially, have this low-level controller that is performing these reflexes, handle all of these mistakes that we could potentially make.
So it's AI.
Yeah, kind of. It's a little bit more designed. So the student who, did a lot of work on this, who also recently graduated, his idea was this hierarchical control concept where, you have this little controller or system operating at the fingertip, then you have additional control on this board which is handling all of the reflexes, and then it sort of builds on top of each other so that the controllers at the low level can handle things or mistakes that the high level controllers would make, similar to how we might operate. Generally the pipeline is we see object, we identify where it needs to be grasped, which is using a lot of learning models, and then there's more like traditional physics-based controllers that are figuring out exactly where the hand needs to go and then how it needs to be grasping it. So it's sort of this hybrid. We use some learning concepts, but then we also use some of the traditional robotics controllers just because of reliability, and sometimes a lot of the learning stuff is a little bit overkill for certain aspects. We also have the ping pong system in the other room, which I can also show. Yeah, so this is the ping pong system. It's probably one of our newer projects. This is what I've spent most of my time doing. We've developed this whole system. We have this gantry that can slide back and forth, and then we have just an arm that's slightly modified from the humanoid, and we have this wrist roll degree of freedom. The whole idea here is, can we explore controllers where we have to make decisions in a really short period of time and have this sort of dynamic manipulation component? So rather than going in and grasping a bowl, we have to plan and think about how we interact with a ball, but we can only interact with it with this little impulse, and that makes it a really difficult problem, and also high stakes, right? If we mishit it, then we're going to lose the point. So we care a lot about precision, accuracy, and speed with this system. And we've been using a lot of traditional controllers for the design of this. but also we're starting to dabble in a lot of the AI reinforcement learning stuff as well. The arm itself is modeled roughly off of a person's arm. We're actually doing a lot of co-design right now about designing a new wrist so that it can operate a little bit more like a person, because table tennis players utilize the wrist to add spin and also kind of fake out their opponent. So like they might make it look like they're hitting a backspin shot, but then change and hit a topspin shot. Like we don't want it to be able to move across faster than a human would, because then it's kind of cheating. We have all these different cameras around here, and that's really our only method of sensing. And we also have encoders on the motors themselves that can figure out where the arm is with respect to the ball in 3D space, but we don't actually need any sort of sense of touch with the paddle itself, because everything's moving so fast that the impact only happens in a very short period of time, and we can't really change anything when the impact is happening. I wish I could demo it. The last time I did a demo, it freaked out. It accelerated so fast that the paddle actually snapped in half, which gives you a sense of how fast this system can move. Right now, because of the power supply that we have, we can only swing at a maximum speed of, I think the end effector is moving at like 10 meters per second, which is very fast, and that's how we can achieve our 20 meters per second return rate when we're hitting. But, you know, a human can smash the ball at like 40 meters per second or something, right? So there are physical limitations that make it not as good as a human.
I am working on a wearable assistive device for older adults to help them stand up and sit down. So basically an exoskeleton, but the idea is that I want it to be something that doesn't use motors or batteries at all, because those are quite heavy, and it's not something that most people, especially older people, want to be wearing around all day. So what I'm trying to do is use kind of clever mechanics to make an exoskeleton that can store people's own energy when they're sitting down, store it in a comfortable way, and then return it to them when they stand back up. So you basically have potential energy. Right? MGH, mass times gravity times height. As you sit down, you're storing some energy. You can put that into like an elastic element, like a spring, and then have it give you that boost when you come back up. Now, what I've got here is an early prototype of a switching mechanism that I'm using. The way that the mechanism works is with cables that are wrapping around these cams. If you're familiar with a compound hunting bow, it's the same sort of thing. I wasn't before I started this, but this is kind of like switching gears. So you have one profile that the cable wraps around for sitting down, where it provides a very kind of steady force, like supporting you as you sit. And then the other profile has a big peak. So right when you get off the chair, it gives you a boost and kind of concentrates all the energy into one force peak. But for it to be passive, I had to come up with a passive way to switch between those gears, essentially. This is what I'm trying right now to shrink it down to.
Oh my god.
So this is not quite ready for showtime, but this is the idea. I have in here this switch that you can push on these switches from inside to go back and forth. And then these ramps, it might not work 100% of the time, but let me see. This will push it back and forth between the two. If it's all aligned, it's a little little herky-jerky right now, but you can use that to transition. So this is the scale size, and I've got some joints in there, these like Revolute joints like you would have on the robot. But to get it down as small as possible, I'm now making a switch with these, they're called living hinges. So essentially a joint that is just part of a single piece and flexes. And you see these all around, especially in consumer goods. So the cap to your shampoo and conditioner, they use these type of hinges because they can last a very long time and they're fairly easy to manufacture from one piece, which will then be part of a wearable device that people have on their legs.
And you'd have to use a different type of plastic because it's bending a lot.
Yes, yeah, so that's been a big challenge, is finding the right plastic. This one is nylon, polyamide 12. It's really been a challenge to find something that's both flexible enough but strong enough so that it doesn't just crack. Like you can see this is flexing quite a bit without breaking, which is a good thing.
Yeah, so this is like a pneumatic finger setup. So this is kind of like the version that we're using now, but this is like a prototype we tried working on beforehand. So it's controlled with air. So right now this is a relaxed position, it's not plugged into anything. But then there's a gas tank over there, and you see when we plug in the air into here, these are like some valves that can pressurize there. The idea is that this will curl up. So there's like 4 fingers here, and each of them can be turned on and off. This is kind of like a switch by each of these valves. So like the idea was you could put your finger in here, or your hand in here, or whatever object you want to grab, and then you turn on the air, everything closes up, and then you can move something around or grab it. So that one's tendon driven with like strings to move it, and this one's using air. The motivation behind this project was like robotic rehabilitation. So if someone's like scapular muscles are atrophying after a stroke, and we want to perform certain like arm movements, like exercises similar to what physical therapists do. So the idea of this was to help like grab onto the patient's arm to perform those arm movements. That's why we wanted something soft to be like passive and safe when interacting with patients. So this is like the second part of the same robotic rehabilitation process. So
It's quite different.
yeah, I somehow always end up in the soft regime. So the idea was one hand, like one end effector, like this robot hand or that one over there, can like move the person's arm around, and this one will help like stabilize the shoulder, so like your shoulder won't dislocate while you're performing those exercises.
In this case, we're just going to show the effect of impedance control. So the robot right now is like just still, and if you try to move it, it's pretty much unmovable.
Yeah, it's
Pretty not much
stiff.
moving. And most of the robots are programmed in industry to just follow their positions, so trajectories in space. And when they do this, they do it regardless of what's in between. So they represent a danger for like anyone coming in between, and that's why they live in cages or in this like kind of safe environments. But our interest is also to use robots to interact with environments where humans can actually like live with robots. And to do so, we implemented in this robot's impedance control, which is a way to fundamentally have the robots present a compliant behavior. So now the robot is in a position, but if you try to move it around, the robot is compliant.
Yeah.
You see? And we can program this. Right now we set some values, but we can change them. And this makes the robot like intrinsically safer to interact with, because now if the robot is moving but it bumps on me, the robot will deformate and change its behavior with respect to what I'm doing. And that actually is very important if we want to have robots interact with humans, like in application as physical therapy or rehabilitation. And so the idea is to implement this kind of control strategies where we can have the robots interact with us. And to do this, there is a combination of software and hardware. So like programming the robot in a specific way, but also having a specific type of robot. So this robot can sense what's happening next to him. So if I stop the robot now, what you can see here, let me check, is that these are the sensors of the robots. And if you touch the robots, you can see that the sensors are moving. You can look at this, come closer. And you can see that even light touch, you can try to touch it as light as possible, and you will see these little scales moving. So the robot has like kind of a feeling of touch. And that's very important because it gives an information about this external environment and how things interact with it.
Now you see that it's holding the end effector in one position, but the rest of the robot is moving. And that's because this is a redundant robot. Basically, to have a position and an orientation in space, you need 6 degrees of freedom because we live in 3 dimensions. So there's the 3 linear dimensions and then rotation about each of those. So 3 plus 3 equals 6. But this robot has 7 joints. So just kind of like our arm, I can hold my hand in one position in orientation, but I can move this elbow. So that means that there's technically an infinite number of solutions that the robot could put the rest of its null space in, but still have this same configuration at the end.
Hi, I'm Neville Hogan. I'm a professor of mechanical engineering at MIT. I'm also a professor of brain and cognitive sciences at MIT. My main research interest is in trying to understand human movement behavior and also try to understand robotic movement behavior. and combine the two of them. If you look at human behavior, particularly if you consider dexterity, humans are spectacularly dexterous, much more so than current robots. And yet, you find that brains are slow, even though we're very clever, but we don't do things very rapidly. Typical neuron communication rate is about 100 meters per second. Typical electron communication rate is about 1 million meters per second. So, huge difference, maybe even greater than that. And muscles are not very fast nor very accurate. So we got this slow, stodgy system that outperforms high-performance, precision robots. So what's going on? What's the trick? And so that's been something that I've been studying for decades. Get some solutions from biology to address problems in engineering, and those engineering problems may tell you a little bit about what the biology has done. And that's a theme that I've played with.
So you're inspired by the human body?
Absolutely. It is spectacularly complicated and spectacularly effective at what it does. You have to keep in mind that it's useful to draw inspiration from biology, but you've got to be careful that biology is not the same as engineering. So we can use insight from biology to help with engineering, and we use insight from engineering to understand biology, but they are different. Okay, so what exciting things are we developing at the moment? Well, on the robotics front, one of the things that we have addressed and solved is how do we manage very high numbers of degrees of freedom. Now, I need to explain what degrees of freedom mean. So, if you imagine your fist, if you treat this as a rigid body, then there's 6 numbers required to describe where it is in space, X, Y, Z, and the orientation in space. So 6 numbers there. If I consider my arm only up as far as the shoulder, then I have actually 7 degrees of freedom, because I can hold my fist in a constant position and move my elbow. But in fact, it's even worse than that, because I can move my shoulder up and down, and my arm really begins at the connection between the clavicle and the sternum. So now I've got 9 degrees of freedom to control 6. And never mind the fingers, that's too complicated. But the main point is, I've got a lot more degrees of freedom than I need. In fact, you've got 200 degrees of freedom in the human body, by a reasonable count. And you coordinate them all. How do you do that? For robotics, the dimensionality of the system, the number of degrees of freedom, makes things really hard. But biology makes it easy. Using a method that's fundamentally based on studies of human biology, we have a method that actually works for an arbitrary number of degrees of freedom. And it works, and we're trying to convince our colleagues that it's the best way to go, but that's a work in progress. So another thing that we're looking at is balance, human balance, especially quiet balance, and how it changes with age. People have studied balance by looking at the response to perturbations. You imagine you walking and you step on a slippery bit or something trips you up. And that's important work, but it doesn't really address what you're doing right now. Is you're standing quietly and nobody's perturbing you, and yet your balance system is very active. So we've been trying to study quiet standing, and we've actually been quite successful in that, and we've developed a description of quiet standing that is accurate. It can discriminate between young unimpaired adults, older unimpaired adults, people standing under challenged balance conditions like standing in tandem position on a narrow bar, and people with stroke, cerebrovascular disorder. And we can discriminate all of those, and not only that, we think we can actually ultimately predict how people age, how their balance performance changes with age, how likely they are to trip and fall as they age, and that, in fact, that's a major risk factor for aging, and basically come up with something that can be easily diagnosed in using limited instrumentation in a doctor's office. Another thing that we're very interested in is the idea of using robots to provide some form of physical therapy for people recovering after neurological injuries like stroke or Parkinson's disease or other things like that. We've done this work in the past. We developed robots that were able to provide therapy. It was a limited form of therapy, just basically moving in a plane or rotating the wrist. But it worked. It wasn't perfect, but it did provide better outcomes than so-called usual care that's provided by a human physiotherapist. What we haven't done so far is to solve the problem of handling movements out of the plane. What this physiotherapists call scaption, there's this movement. And stroke patients often have trouble with that. So what we're trying to develop, and it's, as far as I know, the first time it'll have been done, is to use 2 robots to provide therapy. One robot stabilizes the shoulder, and the other robot works with the hand to help. The assistance is graded, so if the patient can do it, the robot does nothing. If the patient needs help, the robot helps. If the patient needs a bit of help, but not too much, the robot changes how stiffly it insists upon the movement. The reason for two robots is because if you look at this movement, scaption, as you raise your arm roughly above your shoulder level, the scapula, that's the wing bone on the back of your rib cage, rotates in such a way as to permit this large range of motion. But if you've had a stroke, then these muscles that support the scapula are all weakened, and you tend to have the shoulder tends to sort of fall down. If you don't take that into account, you can actually cause joint pain and injury if you lift the limb without managing the scapula. The key idea behind impedance control is that we're not just controlling motion, we're not just controlling force, we're controlling the relation between them. That turns out to have many benefits that became clear with hindsight. For example, a subtlety of the engineering is if you take a robot that's well behaved and well controlled, and then you couple it, you kind of connect to another object, then just the mere connection between those two things can cause instability. This was known since the 1970s, where robots that were good at being able to manage free motion, when you asked them to press on a surface, they would sit on the surface and go and continually bounce off the surface. There was an instability in the control system that came about from the physical interaction between the robot and the thing that it was trying to work with. So if I set up the impedance that how the robot reacts to contact, I can eliminate that problem. Think of impedance as it's like a compliant spring, but maybe with some viscosity added into it as well. Right. We measure position, we measure force, and if you know where you want to be, and you know the deviation between where you want to be and where you are, that then can be multiplied by the impedance operator to give you the force. So if I know force and position and the nominal the place where the force should go to zero, that gives me the impedance. So I can actually estimate it if I wish in humans, and we've done that, or I can impose it with a robot, and we've done that. Right. And you've seen today that you can change you can change it from really stiff to not so stiff to really floppy. In biology, the situation is quite different, and this looks very much like, now what's going on in biology is that you have sensors around the muscles. You have some sensors that measure the muscle length and the muscle rate of change of length, and they send signals back to the spinal cord, and others that measure the effective force generated by the muscles. One of the things that's peculiar is that one of those, the sensor that measures the length of the muscle, tends to excite the muscle and turn it on even more. The sensor that measures the force generated by the muscle tends to turn the muscle off. It goes back to the spinal cord, but makes an inhibitory connection. So it looks like you've got these two competing signals going through the spinal cord, which is about as fast as you can do things in the body, and they're fighting each other. Well, the reason for that is because if the effective impedance or stiffness of the muscle changes, the effect of these feedback loops, these two opposing feedback loops, is to make that less important. So if you have a high gain position and a high gain force feedback, then the combination of those gives you essentially a direct control of the impedance. One of the issues with conventional robotics is that most things I do, the tasks are described in terms of things I want to do with an end effector, like a hand. I want to move here, move there. I need to map that then back into the place where the motors live, right? So if I want that movement, you're going to tell me what the joint angles are and what the motor torque should be. And that's a hard problem, but it's solvable. But I got problems. If I go down to a position like this, where I'm at maximum reach, that's called a singular configuration, because now there's no good solution. So if I try to move in this direction and I just know about this movement, I can't actually figure out what to do with these interior degrees of freedom. Turns out that the approach that we're using, which is based on managing impedance, solves that trivially. So most robots don't operate at singular configurations. They avoid it. They lose something like about 3 to 8% of their workspace by doing that. Our method works not only at singularities, it goes into them, comes out of them, and we can take advantage of the singularity to minimize the load on the robot actuators. It's not that you couldn't do that otherwise, but we have one method that works for everything and works effectively. I think it's great. I know it is. We just have to convince the community that there's value.
That's great, Neville. Thanks for your time.
Yeah, very welcome.